Okay, well, it says it's still recording, but I'm not sure if it is. Okay. Okay, if okay, so does anyone feel like they kind of like at least somewhat have an idea of what dynamic programming is? Or can you guys tell me like kind of like roughly what you guys understand, like what you have to do like from like dynamic programming?
Like the general idea is to solve from like the sub problems, then we build up from there.
Um, okay, that you kind of need to do that. Yes, like that's kind of like a necessary, quote unquote, necessary idea for you to do dynamic programming. But I would argue that that's not really the main thing that kind of like sets it apart from the rest. Because if you do like, for example, recursive backtracking, right, you're still doing this building up from subproblems idea. But it's not always it's not necessarily dynamic programming. Does that make sense?
We want to.
Mm-hmm. Wait, what do we want to do? I think your mic muted itself for some reason.
Oh, we want to
So-
get like not do repeated computations of the same thing.
That's right. So some of
So
the
we store the
problems.
results of the computations.
That's right. So some of the things that you need to one of the key like ideas that you need to kind of like take note of is that sometimes problems require you to recompute the same thing again. So like you guys have seen Fibonacci, right? So if like for example Fibonacci is just very simply like, you know, you want to compute this function, right? F of x is equals to f of x minus 1 plus f of x minus 2. Oh my god, why is my width varying so much? Minus 1. There we go. Okay, and basically that, like, I mean, like, okay, like you have base cases, right? So like maybe let's say f0 is equals to f1, is let's say equals to 1, just for simplicity's sake, right? The point is that when you write this function, like for example, let's say like if you're lazy like me, you would write in Python, you would probably say like define f of n is equals to this, and then you just like return like the f of like whatever, right? And like slot your base cases in here, right? And this is pretty much how you write your algorithm. Now like we've analyzed this, right, in the first few weeks, like what kind of runtime this comes down to. Like if you want to be a bit loose about it, right, you can go home and, I mean, like if you practice, you can try, you would say that this runs in O2n time. But if you're like very, very, very precise, you would realize that this thing runs in like, it's called 5, but it's like 1.5 or something. I don't know. It's like 1 plus square root of 5 over 2 or something. So like put that in here to the power of n. That's the actual runtime. The point is this is exponential. You know, and it seems kind of ridiculous that we're taking exponential time to compute something so basic. You know, and the reason why, the intuition why this is the case is because when your function runs, right, like if I could just trace a little bit of the execution, like I don't like tracing, by the way, I actually really hate it. But where's my eraser? There it is. I don't like tracing, but for dynamic programming, just so that we all see like what I'm trying to get at here, right? If for example, let's say I call, that would be a really big pen. If for example, let's say I call function f on 5, right? It's going to make one recursive call to like f4. It's going to make one recursive call to like f3, right? And then I mean, well, this guy right here is going to make a call to like f2, and okay, yeah, I mean, I guess f3. That's the one that I'm getting at, right? And then I mean, this guy makes like a call to like f1 and a call to f2. All right. The point is that some of these values repeat. Okay, and if you sort of like make this observation and realize that the problem you're trying to solve, right, kind of has an algorithm that does this, that kind of has an algorithm that keeps revisiting the same subproblems, right? It might not be a bad idea to store it. The reason why is because the intuition here is that every time your algorithm forgets, right, it's a very expensive thing to do. So like, for example, if I have to compute if I'm computing f5 and I have to call like multiple times of f3, right? And if I'm not storing it, the algorithm has to just redo all that work, you know? And you can imagine how that would be very expensive, right? Like imagine how, for example, maybe in your A levels or your secondary school, like when you have to do an exam, right? And then like, can you just imagine if like there were like sub problems and stuff, right? Like question 5A, B, C, D, and E, and so on and so forth. And like they're supposed to build off the previous question, but you instead somehow you have like the memory of like even worse than goldfish, and like, you know, you only remember what you wrote in the last 3 seconds or something. Then every time you move on to the next sub question, you need to redo all that work. That's really inefficient, right? And the point is that, hey, we have like, you know, like algorithms like allow us to access memory and store stuff, so why not store stuff, right? So that's kind of that is pretty much like the like one of the things that you need to sort of like save up on save up on running time. The second thing that you need, which I'm not sure whether he mentioned, there's usually I mentioned two things that you need for dynamic programming to apply. So the first thing you need, like you guys mentioned, is overlapping subproblems. That is pretty much a given. Oh, my handwriting, subproblems. Right. The other thing that you kind of need is something called optimal substructure. Did Vash mention this? What do I feel like, you guys are like trying to pull up like the database from your head and be like, did he say this? Run a search
Yes,
algorithm.
exactly like that.
Yeah. Okay. Cool. So basically, in case you're unclear what this is, and the reason why I say you're unclear is because like a lot of people like subsequently when they learn greedy algorithms, they confuse optimal substructure for greedy algorithms because the proof like template is kind of the same, but it's not. It's really not. So optimal substructure means that when you're trying to solve a problem, right? Like okay, like think of it as like, for example, you're trying to optimize for something, which I'll show you a few problems in a few minutes, right? The point is that you wanna do your best in solving your subproblems, because doing your best in solving your subproblems is going to allow you to do your best in solving like your current problem. Now, of course, at this point, you might be wondering, yeah, but like, can't you say that about anything? Like, isn't it obvious that you should always do your best in solving the subproblems? The answer actually kind of is like, not always. I don't want to show those examples now because to explain why it's not easy to see that there's optimal substructure is very difficult and an exercise in and of itself. So just take my word for it. There exist very difficult problems. And if we could somehow if we had like this very nice pattern of there are overlapping subproblems, there's optimal substructure, so on and so forth, and we could solve it easily, then perhaps we'll have an efficient algorithm. But the point is that we're actually very unsure. All right. So just take my word for it for now. Some problems needn't always have optimal substructure. It just so happens that all the ones that we're showing you right now have it. So try not to get the false impression that it's always that way. Yeah. Okay. So let's see. Let me erase this. And I've mentioned what I wanted to mention about like introducing it to you guys. Let me know if it's unclear, by the way, because this is pretty much like the 5-minute. Oh yeah, yes. Question.
Yeah, what's optimal substructure again? I don't remember the prof talking about it.
Okay. So optimal substructure is kind of like, okay, can I give an example off the top of my head? Okay. Tell you what. Let me start. I was gonna start with an example to show you to show you how I use dynamic programming, and then I'll show you how there is optimal substructure. Sound good?
Yeah, okay.
Cool. Okay, so I had to go through the slides last night just to make sure that I don't overlap because I almost did subset sum as well. And then I realized, oh damn, he did it. So damn it, now I need to use a different one. So I'll try to go through a few. The first I'll go through is, let's say, knapsack. And then okay, wait, I had a few installed for you guys. So there's knapsack, I think there's rock cutting, and then let's talk. Okay, let's cover these two first and see if we have time for anything else. Okay, then I'll talk a little bit about the assignment. Right, I don't want to reveal solutions, of course, but I'll try to push you guys towards what you're supposed to look at. All right.
Nice, thanks.
No worries. I mean, that's why I'm here. Erase this. Okay, let's begin. So knapsack, I'm not sure if you guys heard of. It's kind of a famous problem, but I'm not saying it's famous so that you guys feel bad that you don't know about it. I'm saying it's famous so that next time when you guys tell your juniors, if you ever become a 3230 TA, let me tell you about knapsack. It's kind of a famous problem. Now I just it's okay. Look, it's let me just give might as well just give you context in CS, right? So knapsack is kind of like a knapsack. It's kind of like a famous problem, and I think from a teaching perspective, it has very good meme value. Because I get to motivate my classes by teaching you how, hey, you're gonna break into someone's house and you have a knapsack with you, and you need to take out as many valuable goods as you can. Here we will algorithmically teach you how to do that. I feel like CS has a lot of opportunities to teach people how to be criminals. Knapsack teaches you how to how to rob a house. Amortization, if we ever see in this semester, teaches you how to what's the word? Launder money. Okay, I mean this is all going on YouTube, so I hope no cops get called after me. But yeah, anyway, I like okay, so like I think knapsack's a good place to start. So the knapsack problem, like the story, is basically let's say you've broken into someone's house, okay, or I don't know, maybe you broke into your own house, like just if you're like really morally objected against like stealing, and you have a knapsack, okay, so let me draw a knapsack. So I guess my knapsack looks like this. Okay, and your knapsack has some capacity C. Let's call it C. Right, C for capacity. Okay, so this is, let's say some, like for simplicity right now, let's just say it's a natural number and let's say it's greater than 0. Okay, I mean it could be 0, but then this problem will be easy. Okay, now there's a bag that's like this, like in the house, right? There's a set of goods. Okay, set of goods. So goods means like stuff that you can steal, right? Okay, and the goods come in the form of like a pair. So like this is how we're denoting it. Okay, so the ith good, right? The ith item we will denote as vi. Let's use wi. Okay, and I is like, let's say from like 0 to n. So you have n items. Okay, each of them come in the form of a pair. Okay, so this is your value, and this is the value of the ith item, and this is the weight of the ith item. Okay, so what's your goal here? Your goal here is to make sure that so long as you can fit all the items in your knapsack, okay, maximize the value that you can walk out of the house. Okay, so in other words, if I want to write this formally, right, I'm saying that you need to pick. Okay, so let's call this set G. All right, so you need to pick. Let me diversify my colors here. You need to pick a set S, which is a subset of G. Okay, such that. Oh, sorry, I wanted green. Man, I prefer the old software, but I don't have that on Linux. Such that I need to satisfy 2 conditions. Okay, the first condition is that the sum of the weights in S, right? Oh wait, I shouldn't use G here. I should be using. Okay, let me cross this out. I should not be using G here. I should be using N, right? I should be using the set like 1 to N. Pick a set of items, right? That is like in the house. Okay, so that the total weights. Wait, what did I say exist? That's not correct at all. Sum of the weights, okay, is at most C, okay, and I need this to be maximized. Vi is maximized, right? So again, like the point of today's first question is, how do you rob a house efficiently? It'd be really funny if like one of you guys ends up like robbing a house in the future, and then like you guys actually sit down and like run this Python script, Okay, please don't do that. Don't rob houses. I'm not condoning robbing houses. This is just to make sure things are exciting for a 9 a.m. class. Let me erase this. All right. So are we clear on the problem? Okay, so to reiterate, you have a bag, it has a maximum capacity. Okay, I don't care like how light or how heavy your items are. They just have to make sure that it's not too heavy for your bag. Okay, then maximize the total value you can obtain out of this. Are we okay with the problem? Cool. Yep. Thank you. There's like 1 or 2 people who, okay, I appreciate it. Okay, so let's begin. So the point of me doing deep, like mentioning this exercise, is that I want to show you like the kind of like process that I use for DP, in case like it's not clear, it was not made clear to you during the lecture, or if like, for example, maybe it was, but like it doesn't fit with you. Like let me try to give you my take on it, all right? Like how I would teach it. Okay, so the first thing you want to do is sort of like formulate the recursion, or like the recurrence. Right, and I'm pretty sure like Devesh would have mentioned this as well, like for sure. Okay, so what I mean by this, right, is that you want to look at the problem, okay, and I mean you can always design an iterative algorithm for it, but for now let's just try to do it recursively, because I think it's a lot more natural that way. Okay, so the way that I want to formulate the recurrence is I want to ask myself, right, okay, if let's say I had a solution, let's call the solution big F. Okay, now this solution big F, what should it take? It should take in the set of goods G, right? So this is the set of pairs that we want. Okay, that's one thing. And the other thing that it needs to take in is the value C, which is the capacity, right? Now my solution needs to solve for these two things. So if I give you a set of goods and I give you a capacity, you should spit out, for example, for now, let's make it easy. Okay, like you don't have to tell me what the goods are, just tell me what the possible value is. Okay. So let's do that. So if I have this, right, like what should this look like? What should this look like recursively? Okay, so you don't have to think of anything like insanely intelligent, like for the most part, right? At least for this problem, you don't have to. I'm not saying you always don't have to do it, but at least for this one, you can somewhat get away with not having to do that right now. So I think, like, for me at least, the simplest algorithm I could think of, okay, is that if I could call the items, let's say like item 1, item 2, and so on and so forth, just for simplicity, right? I would define this algorithm to, okay, the intuition I'm going to have is that I'm going to try solving it with the first item in the knapsack, see what happens, and then try solving it for the first item not in the like without it in the knapsack, and see what happens. Okay, so the way that I would try to solve it, and I'm going to pretend that the base case is solved, okay, because like that one should be easy, and you guys can do it in your own time, right? Okay, so I don't want to bother talking about this now. For the recursive case, right? Okay, I'm going to try two things. Now the first thing I'm going to try is I'm going to try with first item in knapsack, right? Item 1 in knapsack. Okay, so the way to do this is that I'm going to solve the problem with one less item, right? I'm going to solve it like without item 1. Okay, sorry, as in I want to solve it, but I've already put item 1 into the knapsack, so it should be out of consideration, right? So it's no longer in the set of goods. Okay, but now since it's in my knapsack, right, I should reduce the capacity, like the amount of stuff that I can put in my knapsack by its value, right? So its weight, right? So minus wi. Okay, but since it's in my knapsack, okay, then what I should do is I should just add the value to whatever solution this is, right? So this is kind of like a neat decomposition here. I'm saying, okay, if I put the first item in the knapsack, I can solve for the rest optimally, okay, and whatever value that I had put into my knapsack, just add it to like whatever I managed to solve with or without it, okay? Now this is the first case, but we don't know for now, we don't know, and it could be the case that the optimal solution or the best way to take the items doesn't really involve the first item, right? We don't know, right? Maybe the first item is really bad, you know, and it just happened to be like the first thing that we saw when we were robbing the house. Okay, so in which case, right, we try without. Handwriting. Okay, so still we remove it from the set of goods. The reason why we remove it from the set of goods is because we say, okay, look, I've looked at you and, you know, I've decided I'm not going to take you. Let's consider the rest, right? So it's not the set of goods anymore. Okay, our capacity of course remains the same, and we don't add the value, right? Because we didn't put it in our knapsack. So this thing doesn't contribute to whatever net value we're gonna gain out of robbing this house. Okay, so at this step, right, we've kind of solved two subproblems, but we only need to return one value. So can anyone tell me what I should be returning after I've solved for these two cases?
Maximum.
Yeah, that's right. So remember, we're trying to go for the best value here. So that's exactly right. We need to return the maximum of these two, right? So return max of these two, right? But like, you know, like I've already kind of hinted at with like Fibonacci. If that, okay, so let's just try to solve this. Let's just try to solve this like this way first, and let's say without dynamic programming, what kind of time complexity do we get, right? I mean, I hope it's kind of obvious, but where's my eraser? Let me clear out some space here. Right, let me clear out. Oh wait, that's too much. Okay, let me clear out. I mean, I hope this is clear enough. So I'm gonna like get rid of it. Okay, so what's the running time? Now, like you guys might not be veterans of CS3230 yet, but at the very least, like if you can formulate the recurrence, you know it looks like this, right? -1 plus 01. Right. Now you might be like, for those of you who don't think this is obvious, right? Because this looks like a two part function, like a two-piece function, right? The reason why this is true is because think about what the algorithm is trying to do. It's going to go through all n items. It's going to include it, try it once with it included, and try it once with it not included, right? Okay, so you make 2 recursive calls, and in each recursive call, you reduce the size of the set of goods by 1, right? Of course, you might say, okay, can we early terminate? Like, for example, if C is less than 0, can we terminate? Yeah, I mean, you should terminate. You should return like infinity, for example, right? But, if your capacity is large enough, that you're kind of like bounded by this function, which is, sort of like the main concern here, right? And this, you guys should really know, you can work out to the end. Okay, so this is pretty much the running time of the algorithm right now. It's not really great if your algorithm runs in exponential time. I mean, like sometimes things do, like, like for now we only have like at best exponential time solutions. But this one turns out we can kind of do better depending on some values. Right, so that's the whole point of me like showing this to you. Okay, so we formulated our recurrence, right? We formulated our recurrence. It's not a very intelligent one. It's kind of a recurrence, right? But this is something I can work with. Okay, so the first thing you need to recognize is whether, the next thing you need to do is to recognize whether it satisfies the 2 properties, right? The optimal substructure, and the overlapping subproblems, right? Overlapping subproblems. Oh, look, it's like similar. Okay, never mind. Okay, so why optimal substructure? So if I could just draw it pictorially, let's say this is my set G of of goods, and let's say this is like set G prime with like some capacity value C prime, and this is like, for example, G prime prime, C prime, right? So every time I'm solving for G and C, right, I make 2 recursive calls. Okay, now I need to somehow convince you that I need to do my best when solving the subproblems, right? In other words, right, like I should really like do my best. I should do my best here. Should do my best. And by doing my best, I mean I need to solve it optimally, right? Okay. Now recall that over here, what I've done is that, like, at this stage, right? Okay, I've removed item I. Like I minus 1, like I sub 1. Okay. So how do I prove that I should be doing my best? Okay, and the argument is kind of straightforward. Okay. The idea is that assume by contradiction that I didn't do my best, right? So like, for example, let's say in either case, right? Just assume that, for example, you didn't do your best in either case. So let me just argue it for 1/2. Okay, so assume I didn't do my best here, right? So I have some crappy solution. Let's call it solution, like let's say like bad solution, right? Okay, so assume that like I didn't solve this part optimally and I have a bad solution. Okay, the question to ask is, what happens if I actually solved it better? Right? So let's say that I had like a different solution. Okay, I can't call it solution again. Let's call it G solution. I have bad naming practices. Okay, and this one is better. So what do I mean by better? If it's better, right, the value should be strictly greater than, right? Okay, now so let's say that, okay, this is the supposed solution that I had. Okay, so suppose that to get my optimal solution here, right, to get this as the optimal solution, I kind of had to use this bad solution. Okay, and then I asked myself, what happens if, let's say, I, like, instead of like just coming up with a crappy solution, I actually like got off my ass and like, actually like, did this thing properly, right? Then I'd have a strictly better solution, right? Because that's the definition of being optimal in this case, right? I have a strictly better solution. It gives me better value. Okay. Now, what happens if I solve that properly and I know that this is a valid solution and I substituted that here, like I put that here instead. So now instead of having solution, you have G solution. Well, then this value would increase, right? This value will go up. Does that make sense? Okay, but that's a contradiction. The reason why this is a contradiction is because we assume that we had the quote unquote optimal solution already, right? Which means that it's the best. It can't be improved, right? You can't call 2 things optimal if one thing is strictly worse than the other, right? So we've kind of reached a contradiction. So in other words, what we're saying here is that, hey, like, you should really be solving this. You should really be solving them like optimally. You should really be trying hard. Does that make sense? Okay, no response, but okay, some takes. Thank you.
A little bit lost.
Little bit lost. Okay, which part?
Like, how does this tie in with optimal substructure?
Okay, so the point is that we want to argue, right, that, like, okay, the way that you should see it is that when you're trying to solve these problems, right, you realize that we're trying to after we remove item 1, we're trying to solve without item one optimally, right? Like basically we're calling the same function f onto these problems, right? Okay,
Mhm.
and then from there, what we're trying to say is that, someone might question your algorithm and say, should we really be like, should our solution really depend on the optimal like values of like our subproblem, right? Like maybe he'll tell you, you could be wrong, right? What if it's not optimal, right? Like what if you need a non-optimal solution so that you're optimal now, right? And how we argue that's the case is by saying, look, pretend that you had a solution, right? Pretend that you had an optimal solution here, and it depended on some bad solution like further down, right? The intuition here is that I could swap out the bad solution further down for a better solution, and it only helps my case. That's pretty much the idea. Again, you might feel like this is very obvious, but some problems you would see don't really have this. Does that make sense?
Okay.
Or give some time to think about it, and if it's still not obvious, like let's say after tomorrow, like you can leave a message on Telegram and I'll try to find a different way to explain it. Okay. Now. Okay.
When you talk
So
about optimal, you're talking about like in terms of runtime?
no, I'm talking about in
Oh,
terms of like what are we trying to optimize for? We're trying to get the best value, right? When we're robbing the house,
uh-huh.
right? So an optimal value for this problem is basically like what's the best, like what's the highest value you can obtain. Does that make sense?
But wouldn't a bad solution like it still give you the correct answer?
No, because a bad solution, for example, right? Let's say you have like a few items and one is insanely heavy but has no value, right? Like for example, let's say like it has like nearly your capacity's weight, but it only has value 1. Whereas everything else has like, let's say like weight 1, weight 2, weight 3, but have like, let's say like 1,000 or like $10 million worth in value, right? A bad solution here would be like, for example, to take like the really, really, really heavy item, right? Then when you walk out of the house with like only like a few dollars to your name, whereas you could have walked out of the house with like a few $1,000,000 instead. Does that make sense?
Right, okay, got it.
All right, cool. Okay, so let's see. Oh, okay. So in case you're thinking like optimal here as in like runtime, the answer is no. Like I mean value, like the value that you're returning. Sorry if that wasn't clear. Okay. The next thing, we're done with this. Okay. So the next one is the overlapping subproblem. All right. So overlapping subproblems, again, it looks very similar to Fibonacci in the sense that like if I have like a set G of items here, right? Think about what happens. Like at some point, right? I'm going to remove, for example, some item 1, right? So like when I go down the recursion tree, I have removed one item, but there's also some capacity I need to take care of, right? Like for example, here there could be like GC, here could be like G prime C, here could be like G prime C minus, I don't know. Let's just say for example like 2, right? Then maybe like the next item that you take, right, also is of weight 2, right? Then in that case, you remove one item and you'll be like G prime, like your set now is G prime prime with like C minus 2, right? And this guy, remember, he has to make 2 recursive calls, right? One with item 2 and one without item 2. The one without item 2 would just end up also becoming G prime prime C minus 2, right? So what I'm saying is that pretend I have like, for example, 2 items, right? So like value 1, weight 2, value 2, weight 2, right? Like if you try to run this like recursive algorithm, you realize that like after considering both items, right, you're going to have to recompute the same subproblem again. Okay. Trace it out on a piece of paper if it's not obvious, but that's what you should be getting at. Oh no, close. Okay. So let me erase this. Okay. So we can kind of recognize or kind of realize that yes, there is overlapping subproblems. Okay. And so how should the algorithm look like? Like at this point, right, you've already formulated a recurrence. You've shown that there's optimal substructure and you've shown that there are overlapping subproblems, right? The next step is really simple. All you have to say is memorize. just shout it into the air or something. I don't know, right? But I think saying just memorize is a bit boring. So let me show you how I would do it, like with a table. So I think that's more concrete. Okay, so the concern now is that I want to be able to store I want to be able to store my solution somehow, right? For example, if I've computed this, I need to find a way to store it. And it might not be obvious, right? Like for example, like I have a set of items here. How am I going to use that to tell which part of this table I'm going to use, right? So like, for example, in this case, I actually have a two-dimensional table. Okay, and it's not as if I can tell the table, hey, my set of items now is G. Please give me the corresponding, my set of items is G, my capacity is C. Please give me the corresponding optimal value if you've solved it already, right? The table wouldn't know. The table's only, like, for example, this table is only going to take in two values, right? I and J, right? C is fine, C is a value, G isn't, okay? But the nice thing about this set of items right now, right, is that if you realize the execution of our algorithm, G always looks like this. It always looks like item 1, item 2, item 3, blah, 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 until item n, right? And the way that throughout the execution, what's going to happen, right, is that like the algorithm is really just gonna, let me get yellow out. Why is it not yellow? Yellow, there we go. The algorithm is really just gonna consider this item and then forget, like subsequently down the recursion, it's just gonna forget about this, right? And then after that, like you'll consider this value, then subsequently down the recursion is just gonna forget about it. Make sense? Okay. So instead of using this set to index into the table, which is, I don't know how you would do it. Like the way I would do it, the intuition is that I'm gonna dedicate this dimension to saying items that I've considered. Items I have considered already. Considered already. Okay. And on this dimension, I'm just gonna dedicate it to capacity. Right? Okay. Now we need to deal with our base cases, of course, right? So if I've considered no items, the values should just be 0. Okay. Now, then I'll consider the first item. Then, if I have the first item, what you would do is that if you're like, for example, of like capacity 0, then you can't take any items, so these should all also be 0. Then at this point in time, you should be asking, okay, do I have enough capacity to take the first item? If I do, if I don't, blah 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 blah, so on and so forth, right? The idea pretty much here is that if I'm at some arbitrary cell, right, some arbitrary memory cell in my table, okay, this corresponds to me considering, let's say for example, this is of row I and column J, right? This cell should correspond to me considering the ith item, right? So in other words, right, this should correspond to me like from here onwards, right? Everything else here is out of the set already, okay? And I'm considering this item, okay, and basically I'm with capacity J, so I'm solving for that kind of set, okay? And I'm going to ask myself, okay, so if let's say I had taken this item, what value could I have gotten? If I didn't take this item, what value could I have gotten, right? And if you look at the kind of subproblems the two subproblems that it should be looking at, it should be like directly, like the one directly above it. Why this corresponds to no decrease in capacity, and you're solving a subproblem with these many items. Oh, sorry, I overshot there. With these many items, right? Or you took the item and you reduced the capacity, right? In which case, like it should be like one of these arrows back, like that point backwards. Like the amount of like left, shift that this arrow points is of course based on your weight, right? Because when you took the item, you decreased the capacity by that much. So you should be solving for like that specific subproblem. And then again, like you're like solving it for like a set of like these items, right? Which you should have done already if you computed like, the solution row by row, right? So you think of it as like, I start from this cell, then just sort of like look up and like look left and like for the corresponding values. I mean, if it's the base case, these should all be zeros, but like from the first row onwards, you should start looking up and looking left, so on and so forth. And then basically storing those, like the max of like those two memory cells here, then do the same thing here, right? You look up and you look left, store that here, so on and so forth. That's pretty much what it should look like. Does it make sense? So this is like how you would like formulate a DP solution for knapsack. Are we clear on this? Crickets.
So can we generalize that and say that the dimensions of the array we need to store our subproblem answers is equal to the number of variables that we have?
If by number of variables you mean the number of states, then yes. Right. So that was the next thing that I was gonna do. We still need to analyze the time complexity, right? We have a nice algorithm, that's great, but if we don't know what the running time is, that's still pretty useless on your end, right? So Yes. So like basically what's our running time here? Like the size of the table, right, is exactly what we need to store. If you think of that as a number of variables, which I call the number of states, yeah, sure. Right. The point is that our runtime, right, is bounded by the size of the table. Right. Notice that like the way that I drew it, at the bottom right corner is where the solution is. Okay. And basically this is the value that we want. Okay, so by the time we finish computing the entire table, right, we're definitely done. And we know that the size of the table, right, is C times N, right? N here because it's the number of items, right? One row for each item, and then like one column for each value, for each possible value of the capacity, up to C, right? So your runtime should just be theta and C. Okay, now I've made a very, very strong assumption here. Like I've made one assumption here so that I'm telling you that the runtime is NC, right? So let me show you my argument, right? My argument says that like my argument part one says that table size is equals to N times C, right? And then I said that from there, I said, okay, therefore runtime is equals to theta NC. Okay. Now, this analysis is correct for this algorithm. But in general, right, let's say that I had a table of size NC. Can I always say the runtime is theta NC?
Does it depend on whether you fill up the entire table?
I mean, let's say I do fill up the entire table. I mean, that's how I get NC, right? Like, yeah. So let's say that I have to fill up the entire table. If you didn't have to fill up the entire table, you could have made the table smaller, I think. But you know, let's run with this for now. Table filling up is not filling up the table is not really an issue. So what's the key assumption I've made here that is correct in the analysis of this algorithm, which may not be correct like overall?
See, the work to fill up individual cells is O1. That's
Exactly.
why you get NC.
So remember that exactly. So remember that like to fill up the value of a cell, right? What are we doing? We're doing the max, right? Of like the one above it and like one to the left, right? And again, this left shift is based on the weight of this item, right? So if, like, for example, the weight here is 2, I should be shifting. I should be looking at this guy, right? If the weight here is 3, I should not be looking at this one. I should be looking at this one, right? I take the max of those 2 memory cells, right? Now max is like for us right now, for all intents and purposes, is an O1 operation. You're exactly right. So this is the thing. I've assumed that like filling up each cell takes O1 time, and since there's n times C cells, now all I have to do is fill up all the cells, right? This is ONC, like theta NC. Okay. There are dynamic programming problems which I can mention later on in the chat where this is not the case, where computing some memory cell actually takes you like a non-trivial amount of work. I think I taught that last semester, but yeah, I mean, I didn't have time to cover that today because that algorithm is very, very, very involved. So basically this is pretty much the kind of workflow that you should, or like the kind of like thought process you should expect if you want to solve a dynamic programming problem. Does it make sense? Okay. Let me. What was the other problem that I promised to show you guys? Jeez, I don't remember.
The rod cutting.
Yes, rod cutting. Okay, he didn't cover rod cutting, right?
Nope.
Awesome. Okay, so rod cutting, I think kind of like follows kind of similarly. Now this problem is a bit weird, or at least I feel like the story is a bit weirder than robbing someone's house. I think robbing someone's house is a very natural thing to consider. Okay, I don't know. don't cut that audio clip out of context and then just like send it to the cops, right? Like they'll think I'm a sociopath. Like, oh, you know, this guy doesn't see anything wrong with robbing a house. What's wrong with this guy? But okay, anyway. So the rod cutting problem is kind of like you're given a rod and you're supposed to cut it. Oh wow, gee, you know, why did they give it that name? You know, like I totally couldn't tell what we were supposed to do from the name. But the interesting portion comes in the fact that the way you want to do it is that you can intuitively think about it as people trying to pay you for like specific rod lengths. All right, so like they give you a rod. Let's say the rod is off length, I don't know, let's say L. Okay, and then you're given a set. Let's call it again V, so like V1 to VL. Okay, now the point is that this tells you like, actually I don't need this, I just need the set, right? Yeah, the set already tells you enough. Actually, do I? Yeah, okay, no. Let's just put that in there. For like, you don't need it, but anyway. This tells you the length of the rod. Okay, and this tells you, right, the value if you were to cut it into a specific length. All right. So the intuition you can think about is that maybe there are like many companies that really want you to make steel rods for them. Okay. And if you give it to them of like some length, right? And let's say these are integer lengths. I don't want to deal with real numbers, right? So these are integer lengths. If you give it to them in like specific lengths, they'll pay you a certain amount for it. You know, you can, the intuition here is that you could think of it as like some company wants it like specifically like this, like maybe let's say of length 5 meters, and if you were to give it like let's say 10 meters, right? It'll be a bit unhappy about it and pay you less, for example, right? Maybe that like a construction company say, okay, I need it exactly at 5 meters and so on and so forth. All right. So they'll pay you specific amounts, and you know, you can think of it as you start off somehow, for some weird reason you started off with like a really long rod, and you're trying to like cut it up for all these people, right? And of course, since you're a businessman, you know, you want to like again make the most money possible, right? So yes, teaching you all about the money. So the question is how would you do it? See, the difficulty here is that if you try to do it the slow way, you could run out with like some n squared or like maybe some exponential time algorithm, right? By the time your algorithm is done, right, these companies probably would have like cut the rod themselves or like look for someone else to cut the rods for you, you know, like for them, right? And you would have made no money. So of course you need to do this quickly, right? So step one, formulate the recurrence. So what should the recurrence look like? So this thing takes in, let's just say like set L and value L and set P, right? Okay. Now the thing about it is that you can try to think of it as a problem where what you do is you try to decide where to do a cut. Okay. And for example, you could say, okay, you know what I'm gonna do? I'm gonna cut here. And after I cut here, right, what I want to do is I'm just gonna call F on this remaining portion. Okay, and then this portion, right, I'm gonna sell it as it is. Okay, so on and so forth, right? Then what's going to happen is that if, for example, you ask again, okay, so let me show you how it overlaps, right? Because I don't want to repeat the same argument later. I think it's easier since I'm drawing it now. Okay, like for example, right, at the beginning of the execution of your algorithm, you might think, okay, I'm gonna cut here of length 1, right? And then the remaining portion I'm gonna call, like do this recursive call. And this recursive call, right, is going to, I know we're not supposed to trace recursive call, like recursion, but like I need to show you how it overlaps, right? So like this recursive call, you know, it's not gonna see the right half, right? This is the rod that it sees, right? And then it's gonna be like, oh, you know what? Let me like, you know, in its execution, someday it's gonna like go like, oh, let me just cut here, and then call a recursive call on the rest, right? Okay, now imagine going all the way back up the recursion tree, right? Back to our original call, right? Where we were, okay? Instead of cutting here, right? We eventually would cut here and call like the same function, right? But you see, this thing has already been solved like the first time we went down, right? Okay, so it's gonna be like really expensive to call it again. Okay, I think this might be worse than Fibonacci, or actually I think it should be roughly Fibonacci. I'm not very sure. Like, I'll work out the details in case you're curious, and then we can have a discussion about it. Right? The point is that it's really slow. Okay, so but the point is that, like, for example, if you've already solved it for this, if you've already solved it for this case, right? I don't see why you need to recompute it, right? You can store that into a table again. Okay, so how should we formulate this recurrence, right? We should say something along the lines of, I don't really want to write the code for this, but it's kind of like for like I equals like 1 to L, you know, like basically we're sliding this blade, right, like along the rod, and eventually every time we make like one step, we do a cut. Then we ask, hey, how much money can I make out of, how much money can I make out of you, plus if I sold this thing like exactly as it were, right? So if I were to do that, right, think of it as like me iterating from the front to the back or from the back to the front, doesn't matter, right? Like the lengths here, like, you know, they don't change. Okay. You know, and then basically what I'll do is that I'm going to recurse on this, right? I'm going to recurse on like L minus I. You can pass the entire set in. I don't think it really matters that much. It's probably not that important. I mean, you can still like subtract, like remove like the items, but that's not really the point that we're trying to make here, right? And then basically, if we cut it, right, we have to sell it. So if we're selling it, we should be looking up what VI is, right? This is our value. Now this tells us, like, for example, all the possible cuttings that we can do and all the possible values we can get out of it. But again, since you and I are businessmen, we want to make money, right? So we should be returning the max across all of these, right? So this is the blackboard scribble of what you should be, the rough idea of what you should be seeing. And I think the optimal substructure argument, let me leave it as an exercise to you guys, since I'm slightly running out of time. Okay, so the point here I want to get at is the DP. Now, what's really being repeated here? I know I've phrased it as a two-place function, right? Like I wrote it as like FLV. Okay, but really the only thing that matters is this one here, in terms of like, how many possible configurations or how many possible states there are, right? Okay, so what I mean by that is that, like, this guy, like, if I have a rod of length like 5, right, the table, like this price table is not changing anytime soon, so I don't really have to care, right? This price table is just for me to look up and realize like how much money I'm gonna get out of selling like a rod of that length, right? So this problem is slightly easier. All I need is like a really long array of like length L, like, of size L. And and each portion should just, like, for example, at index I should just be storing how much money can I make, right, if I was given a rod of length I. Right, this is pretty much it. So if I want to solve my problem, right, like basically just like, in the base case is if I have a rod of length 0, I'm guessing this should be of 0 value, right? No one's going to give you money for free. And then, like, for like the subsequent ones, all you have to do is sort of like for every value here, you just need to iterate it back, find the maximum of those, and then like chuck that in here. Right? So if I were to just do this naively, right? What should the run, like, as in like this is my algorithm, right? This is my dynamic programming algorithm now. What should the runtime of my algorithm be? Let's take a few guesses. While waiting, let me write the data. What should the runtime of my algorithm be? Oh, is my algorithm not clear right now? Do you guys see what I'm doing? To compute the value of a cell here, right? I need to iterate back, find all these values, and find the maximum of them, right? And then, like, as in like not just the maximum, right? But like, for example, like I take this value and then I have to like plus the corresponding length, like difference here, right? Then take the maximum across all of those and put that in here. So what should the runtime of my algorithm be?
Is it linear?
Is it linear? A bit too small. You're not accounting for some of the work.
N squared.
Sorry?
N squared.
Yeah, I mean, well, actually, in this case, I kind of made the mistake of not using n, but so L squared. But yes, L squared, right? Because there's L cells, right? And the way you can think about it is that at this cell, you kind of have to iterate back once. This cell, you have to iterate back twice. This cell, you have to iterate back 3 times. This cell, you have to iterate back 4 times. This cell, you have to iterate back 5 times. This one, you have to iterate back 6 times. Blah 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 blah, right? So it's kind of like this summation of I equals 1 to L, right? This is just like O of L squared. So that's your runtime. All right. I mean, I'm running out of time, so I can't like elaborate too much on this, but that's basically what you should be seeing. So like if I could, like, if it's not clear now, think about it a bit. If it's still unclear, ask me a question on Telegram, right? And I'll try to clarify. Now, as for the assignments, right, that's pretty much the advice that I would give you. Like for the most part, right, when it comes to the design, formulate the recurrence first. You don't have to worry whether it's a dumb recurrence. It just needs to solve the problem, right? That's the first step. Second step, right, do the two things, right? Check whether using this recurrence you can overlap the subproblems overlap, right? So I don't want to say too much about the subset sum one, the multiplication one, right? The one to hit the target T, right? You want to think about how if I was given a sequence of like numbers, right, like A, B, C, D, E, right, so on and so forth, right? You want to think about how, like, like for example, let's say I did a cut here, right? Now this is a value G here, and I want both of these guys to become T, right? So what should this guy be, like, so on and so forth. That sort of thing, right? Like, what should this value be so that if this guy and this guy hit, you get T, so on and so forth. So and you can see the overlap, right? The overlap is that every time you start asking for the same cut from the same guy again, right? Then you start having this what's the word? You start having this overlap. Yeah, sorry, I was spacing out. Right? okay, there's a bit more thought into it, right? The algorithm's supposed to run in like n cubed k square or something. Like the hint here is that you kind of need to iterate through all the group elements. Like once you start drawing like this divider in the middle of like the groups or something, you need to like say, okay, can I hit this value and can I hit this value? Then you try something else, right? Like to hit t, you know, like you could have like multiple values here and multiple values here. Each of them, when you pair up, you will hit the value t, so on and so forth, right? So you kind of need to like think about it like that. That algorithm isn't very smart. It's just that you need to kind of like try to whack out all possible combinations and then somehow store them in a nice way. All right. What other questions were there? I think that was like the binary bracketing one. The binary bracketing one, I would say A and B are easy. C needs a bit of an observation. You kind of need to relate it back to the binary bracketing case. That's what I would say, right? But it is kind of difficult. Can I say more about it? You want to think about how you can relate it back to the binary bracketing case. I would say that there's like a quote unquote one-to-one correspondence if you eventually see it. Yeah. Okay, what other questions were there? The subset one I don't want to talk about. The group one, there's the matrix one, right? So the matrix one might be a bit messy. But I guess like some of the thoughts that you should already have if you've not, right, is that you want to think about, if I have a grid, like let's say this is my original grid. Okay, that's too big. Let me make it smaller. If I have some original grid, okay, and I have let's say, I mean, I'm not saying that you only have one DP table, but let's just say for now you only have one, right? You want to think about this location here. Like for example, if I were to pick a memory cell here, right? Okay, for some I and j, right? You want to think of it as the problem. If I were to just look, like if I look from 1 to I, stop at I, and if I looked at 1 and stop at j, that sort of thing, right? This is what you should like try to work towards, right? Think about like the kind of things that, okay, you know, if I'm here, right, what should I be solving? You know, what should I need to see? Like, what should I need to solve recursively so that I get this, you know, so that I can solve this problem, right? Then save all of that into a table or two tables or whatever, like however many tables you need, as long as you don't exceed like, you know, n squared space. And then there, yeah, that's pretty much it. Right. Then as for analyzing running time, like I've mentioned, you kind of like, it's like as a general idea, it's supposed to be the number of states multiplied by the amount of time it takes to compute every single state. That's about it. All right. Any questions? No, because I need to run off to the next class already.
Quick question, not related to this one actually, but just now for the knapsack question, you used when you analyze the recurrence, you change the two variable
into one, right?
into one. Yeah. How do you go through that idea again? The thought
Okay.
process.
So the idea is that if you think about it, right, like if like sure you could potentially like quote unquote early terminate, right, if you hit like a if your capacity like hits 0 like somewhere through the recursion, right, like maybe let's say for example you took the first 10 items and all of that already took up your capacity, then you actually don't have to recurse anymore, right? For example, because like t and like some negative value here, you end up like doing that. You shouldn't, like, you know, this should just give you 0, like should just give you infinity, that sort of thing. But we care about, for example, the potential that C could be like, you know, like much larger, right? And you could potentially take, for example, most if not all of the items here. And quote unquote, that's where the challenge lies. I mean, I wouldn't say you can take all the items because then the problem would be trivial, but you know, like you could take, let's say for example, most of them, right? And so the point is that like, for the most part, you're going to roughly be doing, okay, it's technically it's technically an upper bound, right? It's just very difficult for me to show you that it's a tight like upper bound in terms of the running time. So if you could just take my word for it, like if you wanna analyze this, then you should just think of it as like, okay, most of the time we're taking most if not all of the items. So just think of it as 2tn plus tn minus 1 plus O1. Does that make sense? In other words, right, like the running time shouldn't depend too much on the capacity. in truth it actually does. And some of the optimizations that you would see for knapsack, which is a very, very well studied problem, end up relying on this fact. Like sometimes people realize that, hey, if the capacity is smaller, there's actually faster algorithms out there. And it's really cool. Some of them are like, okay, we're gonna do this greedy strategy where we know that we can't take too many items because the capacity is very small. So we're going to like sort out and quickly prune out like items that shouldn't be considered in the first place, that sort of thing. Those algorithms kind of exist, and their running time is like bounded by the capacity instead. So for this one, this really basic one that I've shown you, just take it as it is, that like this is kind of a loose upper bound, yes, but it'll be very difficult for me to prove that it's like any tighter upper bound, in my opinion.
Okay.
All
So
right,
just
yeah.
assuming that we solve have infinite capacity and it's not of our concern.
Yeah, I mean, for running time, yes, but of course, like when you're solving the problem, like in
Yeah, of
its
course.
actuality, like it doesn't have infinite capacity, right? Because like
Right, yeah.
because if it did, you should just take everything. I mean, that would be a really weird universe where you can like steal someone's car and TV, and actually no, you can put the TV in the car, but oh no, we're putting the car in the knapsack. Oh, well. but yeah, that's basically it. All right.
Okay, yeah.
Okay, if there are no other questions, I'm gonna run off to the next tutorial now. See you guys next week. Ask me if you have questions on Telegram. All right.
Thank you.
Thank you.
No worries. Bye bye. Oh, I need to end the recording. Stop recording. Yes.